Okay, what do you think? What do you think would be an example of like a finite interval? What do you suppose that means?
It starts and it ends.
Starts and it ends. So it's got two endpoints. So something like, oops, something like this maybe. That's just one example of a finite interval, right? It's got a definite left endpoint and a right endpoint, and it only includes the values in between, and in this case, also includes the right endpoint, right? What about an infinite interval? Never ending. Okay, so how many endpoints might it have? Might have one, right? It could have something like, maybe like this. It's got a right endpoint, but it goes forever to the left. Could even have, how many endpoints? None. Could just be the entire real number line, right? That's an interval, okay? All right, so there it is. All right, so an interval is part of a number line. Let's make that a little bigger for you, how about? Is that better? Everybody see that okay?
Yeah.
So it's part of a number line without any breaks, could be finite, could be infinite. Let's look at a couple examples. So what if we want to look at an interval that's going to include all real numbers from A to B? A and B don't sound like numbers, right? That's all right. We're just going to leave them as variable numbers. A is going to be the lesser of the two numbers. So if I wanted to maybe make a graph of this number line, what do you suppose it's going to look like? There's my x-axis. There's two values. Which one would be A? Left one, good. So A goes there, B goes there. We want to include all the numbers from A to B, including A and B. So what would that look like? Solid endpoints, connect them, right? Good. So something like that, right? Okay, finite interval. What we want to look at first, really the first big issue that we got to deal with is how do we represent these intervals? Right? What are some ways that we can say those intervals? Well, three ways that all mean the same thing that we're going to talk about today are going to be inequalities using set notation and interval notation. Inequality is the one you're probably most familiar with. Does it make sense that that inequality corresponds to that interval that we've drawn? How do we say this is a compound inequality, right? There's two inequalities mushed together into one. We've got the inequality x is greater than or equal to A, and the inequality x is less than or equal to B. They both have to be true. So does anybody know how we actually say that inequality then? So it's, okay, you'd think that you'd start on the left and just read across like you would a book or something, right, or an equation. So you think you'd say A is less than or equal to X, which is less than or equal to B, or something along those lines. But you might remember, we talked about this a little bit in geometry, but this would have been probably more in Algebra 1 topic. You always want to start in the middle of a compound inequality like that. So we'd say X is greater than or equal to A and less than or equal to B. That makes sense in terms of our picture, doesn't it? We've graphed in purple a set of x values. We want to describe that interval of x values. Well, those values that we graphed are all greater than or equal to A, so starting at A, moving to the right, and less than or equal to B, starting at B and moving to the left, right? Does that make sense? Notice that the way we write this matches up well with what the graph actually looks like. The A is on the left, the B is on the right, and what is the significance of this equal sign that goes with the inequalities? When we say x is greater than or equal to a, what does the equal part mean?
It could be on A.
So it could be on the endpoint, yeah, right, we include the endpoint. And so that equal sign just tells us that that is filled in, right? And that equal sign right there just tells us that this endpoint is filled in, right? See the connection? Okay, if you know how to write an interval as an inequality, the next one is just an absolute given. It's virtually the same thing. If we want to take that same interval and express it using set notation, this is what it looks like right here. There's really only two differences. What are they? In moving from the inequality to the set notation. The inequalities actually that we just wrote is included in the set notation. What are the other two parts though that you see? What about on the ends? You get brackets, right? The script brackets. Why are they there? Well, that's how we say set. A set is always enclosed in those squiggly brackets. Those are set brackets. So a set of something has to be contained in the brackets. So there they are. We've got the left bracket and the right bracket. Then there's one other part. There's this part out front. This X bar. What does that X bar mean? We would read that in math like this. We would say this is the set of values of X, the variable X, and that bar just means such that X is greater than or equal to A and less than or equal to B. Okay? But sounds complicated. In practice, it's not. All you have to do is take your inequality, slap brackets around it, and put an X bar out front, and you've got set notation for the same interval. Okay? Last one is this guy, interval notation. What do you suppose, can somebody take a stab at connecting that to the interval? What are the significance, you think? There's really a couple things going on here. We've got the A and the B, and then these square brackets. Any idea what all that stuff means?
Everything in between.
Okay, so yeah, the A, pretty clearly goes with the left boundary, right? The B goes with the right boundary, and we're collecting everything in between, and the square brackets indicate that we are including the points. If those were rounded brackets, it would mean that we weren't including the endpoints. Okay, make sense? So this just says all values greater than or equal to A and less than or equal to B. Okay, let's try another one. What about one like that? All real numbers greater than A. So if I were to graph that, let's say that's A, what's it going to look like? X is greater than A. What do you think? Open circle. And which way is the arrow going to go? To the right. Greater than to the right, less than to the left, right? So that's supposed to be an arrow. Whoops. That's my graph. Makes sense, right? We're used to that notation. If we want to turn it into set notation, all we do is slap the set parentheses with brackets around it, throw in the X bar at the front to declare the variable. What about this though? That looks a little weird. Somebody explain that to me. Say it again. Right, okay, so it's going to start, what this is telling us is that we've got a left boundary at A, but there is no right boundary, right? It just extends infinitely far to the right. So it's unlimited to the right. Does that make sense? Why is it a rounded bracket this time? Okay, but the rounded bracket has to do with what the endpoint looks like. Remember, it was a square bracket in the previous example where we had solid endpoints, that we were including the endpoints. Why is this one rounded?
It's open.
Yeah, it's open. Doesn't include the endpoint. Okay. Now, infinity's tricky. We use it a lot. We can use it a lot in this section. What is infinity a number? Not a number, is it? It really isn't a number. Sometimes we mistakenly talk about it like it's a number, but it's not. What does it mean? Yeah, just unlimited or unbounded or so whatever word you want to use, but it just means it goes forever, right? So would it make sense for me to replace in any circumstance, could I replace that rounded bracket with a square one? What's the problem with that? I see some head shaking. That's correct. What's wrong with that? If it were a squared bracket, that would imply that there was an endpoint here, right? We're including an endpoint, but you can't because infinity is not a number, right? There is never going to be an endpoint to the right. Make sense? All right, so, and then by the same token, if we wanted to say all numbers less than or equal to A, does it make sense that that's what the interval notation would have to look like? Because now we're including the endpoint, right? And it's a right endpoint. We're going to start at A and include values to the left. So we have an endpoint at the right, we have square brackets because we're including the endpoint, and then the interval just goes forever to the left. Right. Okay. So, oops. So we already talked about this, but this is, you can, when you're going through the lesson on your own, if this is a little review, remember that for this set notation, that just means the set of x, real numbers x, such that x is greater than or equal to 2. No big deal. We talked about that. And then remember that square brackets include endpoints, parentheses do not. Okay? So try this. In your notebook, quickly see if you can take these two intervals that are graphed and write those intervals, each of those intervals, into 3 different ways that we talked about. Yeah. It is, yeah, right there. That's an open circle right there, where I'm pointing. Okay, so what do we got here? Let's see. So let's take we're going to look for an inequality for the left one now. What do you think, Cyrus? Which one of these, 1, 2, 3, or 4, top is 1, let's say, which one of those do you think is going to best match that interval? Yeah. Everybody see that? Everybody agree? Okay, that's good. Because we got solid endpoints, so we need to include the equal signs. Okay. Tyler, what do you think for this one? Or the left one, it's hard to see, but that left one is open and the right one is closed. Number 2. Okay. Looks good. All right. Now notice if we get the inequality, then set notation is given to us, right? Piece of cake. We just add those extra pieces and we have the set notation. What about interval notation? So let's take the top one and the bottom one here. The top one, Maisie, so which of these choices would I select for that would correspond to the top one?
The first one.
First one?
Yeah.
Okay, everybody agree? You got a different choice? Valerie's shaking her head. What do you think? Which one? Last one. Okay, what's the difference? Did you see why?
I couldn't tell.
Oh, okay. Okay, yeah, you see now, it's hard to see.
Okay, now I see.
You got it?
Okay,
Okay, because these are the square brackets. Okay, good, good. Sir, what about the bottom one? Third one, good. Everybody see that? Okay, good. All right, so we got the table completed. If we want, let's just really quickly, let's look at, how about just one of these? We don't need to do both. Infinite interval. How about this one right here? The one I'm pointing at, the left one. Which choice is going to fit that best? Jasmine, what do you think? It's going to fit this one best. Right here?
No, wait. The third one.
Right here?
Yeah.
Okay, x is greater than or equal to 4. Okay, maybe, no, okay, you're close. Is it the second one or the first one? Now, it's hard to see, but that's a closed circle. So, okay, the first one, how about, right? How come? So we're going to graph, the endpoint is at the right, so the values in the interval are going to be the ones that are going to be less than 4, because the 4 is the upper boundary. Does that make sense? So if we want to include just the part that's graphed, we want to use 4 is the magic number, right? 4 is the number that's going to separate the values that are not in our interval from the values that are in the interval, right? Well, if I want to start at 4 and I want to describe the values to the left of the endpoint 4, remember that when we're talking about inequality, a less than inequality means the values that are to the left of the boundary, right? For example, 1 is less than 4, so 1 is included in that boundary. Right? 1 is an x value that works. So this has got to be the one that works. We want all the values of x that are less than or smaller than 4, including 4 because it's shaded in. Okay? All right, so what would this one be then? What if we started with an open circle at 4 and went to the right? So bigger values now. Yeah, there's the last one, right? Values greater than 4, but we're not going to include the equal sign because it's an open circle. We're not including the endpoint. Okay, so what about the corresponding interval notation for that? Bailey, what do you think? For that top one, which is going to be the interval that goes with the top one? First, second, third, or fourth? And that's a closed circle. Oh, is it? I'll make these bigger. Let's see, where are we? Right there. Okay. So if we're looking at this one, if it's a closed circle, we're going to want an open bracket or a square bracket, parentheses or a bracket. No, okay, because the parentheses are with open circle, right? Bracket. Here's a way to remember that too. I have a tricky way to remember that. It takes more ink to draw a closed circle than an open circle, right? It takes more ink to draw a bracket than it does parentheses, right? So we know we want parentheses at 4, and we're picking values that go to the left forever. So what's it going to be? Second one. There we go. Okay, makes sense. What about this one over here? So now it's an open circle. So it'd be the third one, yeah, right? So we're starting at 4 and going to the right forever. The left boundary is 4. There is no right boundary, and it's a rounded parentheses because it's not inclusive of the point. Very good. Okay? So we got it. Okay, next issue then is we want to connect the concepts that we just talked about to domain and range. What's this doing? So, quick reminder. Okay, we know that remember that the domain of a function is the set of all the input values or the x values. The range is the set of all the output values or the y values, and f of x is just fancy name for y, correct? All right, so if we look, I'm going to show you one little quick trick for remembering that. Oops. Is that it? Yeah. Here's a way to remember that. Just keep it straight. We won't worry about dependent and independent. Let's get rid of those. We won't talk about that for a while anyway. But when we're trying to connect domain, the set called the domain and the set called the range, think alphabetically. D comes before R, so domain before range. X comes before Y alphabetically, and I comes before O. So it's always alphabetical if you want to line those up and try to remember which one goes with which. Okay, so domain set of x values, range set of y values. Now the end behavior, we talk a lot about this like in my calculus class. End behavior, we're referring to what's going on way out to the right or way out to the left on the function. Sometimes we'll talk about the tails of the function, what's going on way out at the extremes. Okay, so let's skip down to this one. So here we got a graph. Okay, this graph, it's a tricky looking graph. It's a graph of an exponential function, f of x equals 3 to the x, but we don't care what the function is in this case. We're just going to try to figure out, based on the graph, what is the domain and the range, okay, to start off with. So the domain are all the x values. So what do you think? What does it mean if we look at this red graph? What does that arrow mean?
Infinite.
Yeah, it just goes on forever that way, right? Same thing up here. It's just going to continue that trend forever. So what do you think if we're talking about the range of, or not range is a bad word, about the set of x values, the domain, is there going to be a lower boundary to the set of x values we could pick? Do we ever have to stop? I mean, could I take a value? Obviously, -2 works for my function. -4 works for my function. Would -10 work? Yeah, it would. Would -1,000,000? Sure. -1 trillion? Yeah. There's no limit to how far left we could go on that graph, is there? Right? What about to the right? This is a little trickier. We can see that as we move to the right, if an ant were walking on this function, as he moves to the right, he's climbing up a steeper and steeper hill. But is there any reason that he would ever have to stop moving to the right? No, right? As he walks to the right, he happens to also be going up, but there's nothing telling him he ever has to stop moving to the right. So then what do you think, based on what we just said, what's an inequality that would make sense for the domain? There's probably 2 of them up there that might catch your eye. Casey, what do you think? We said we could go forever to the left, right? So there's no smallest boundary for an x value. The x values could increase forever, right? So which one do you think is going to fit? Which one? Number 1? Okay, 1 looks good. There's one issue with that choice, though. Look carefully at it. Look at the inequalities. What's wrong with the inequalities? Ah, they've got equal signs, yeah. Third one, right? Equal signs don't make sense because we could never equal infinity. It's not a number, right? Look, tricky, right? Tricky. So what if we chose set notation? Well, set notation, that's pretty obvious. It would just be that one, wouldn't it? right? What about interval notation? What do you think? Interval notation.
Would it be the one in the parentheses?
Parentheses, yeah. So the top one, right? Yeah, good. Okay, whoops. That guy, right? What's that mean? It means there is no boundary on the left, it goes forever, and there's no boundary to the x values on the right. Make sense? Okay, let's look at the range. So now we're gonna look at the y values. The ranges are harder. They're harder to find. You have to use a graph to find the range just about. You can find the domain in other ways, but we gotta use really the graph to find the set of y values. Okay, what's the lower limit of the y values appear to be?
1.
So there's 1 right there. It looks like I can go a little bit below 1. What does it seem to be? 0. Yeah, it looks like if you follow this function to the left, it looks like it's gonna dip down and approach the x-axis, but never really get there, right? That'd be like the example we looked at yesterday, where if I'm stepping towards the door and cutting the distance in half with every step, do I ever get to the door? I never get there, right? I just keep approaching it, but that's the one place that it's kind of the limit of my motion, right? Same thing here. The y value, the smallest y value that we approach is 0. What about the biggest y value? If we walk the other way, this function appears to just go up without bound, right? So which one of these then, which inequality fits our range? Yeah. Does that make sense? Third one? Gonna be greater than 0, but unlimited upward, right? So what's the corresponding interval notation?
The last one.
Last one. Yep. We have a left boundary that doesn't include the endpoint at 0, right? There is no upper boundary. One way to think about range is to kind of think about looking from this perspective, right? So if I turn my head, where that's going to be the negative direction and that's the positive direction, what would I see if I turn my head like this and look at that function? I see that it stops at the y value of 0 but goes up forever, right? Okay, last issue here. This looks kind of strange. Weird notation. What do the arrows mean? This means approaches. Okay, so which of these statements makes sense when we're talking about end behavior? And that's important. The end behavior, remember we described as the behavior way out there or way out there, right? So end behavior has to start with something like, as x approaches positive infinity. So if we go infinitely far to the right, what does the function do? Or if we go infinitely far to the left, as x approaches negative infinity. So this one doesn't even make sense as end behavior, right? Because x is just sticking around right in the middle. We want it to go way out in those directions. Let's check the next one. Does this work? As x approaches infinity, f of x, or y, approaches infinity. Let's see if that matches what happens. As x approaches infinity, positive infinity, so as we go infinitely far to the right, y approaches positive infinity. Is that true? It is, right? As the function goes to the right, it also goes up at the end, right? So that works. Okay, that's a true statement. Whoops, wrong one. That one. What about this one? As x approaches negative infinity, so what does that mean? As the ant walks infinitely far to the left, f of x approaches negative infinity. So that'd be saying as the ant walks infinitely far to the left, he or she also walks infinitely far down. Is that true?
Yes.
It doesn't seem right, does it? As the ant walks infinitely far to the left, the ant just kind of stays at a y value of 0, approaches 0, but does not go clear down infinitely far downward, right? So that one doesn't work. What should it say? As x approaches negative infinity, f of x approaches 0. Yeah, approaches right. There's our y-axis. That's y equals 0 right there, right? Okay. All right. I think
That's a lot for one day.
There's a sign. That's enough for one day. Okay, here's what my plan for tomorrow.